Alright, so in the previous video for Math 1560 Calc 1 at U of L for fall 2017, we introduced the idea of a Riemann sum, this way of adding up the areas of these rectangles that we obtain once we choose a partition for our interval and evaluate our function. And now we're just going to look at a few examples to show you how these Riemann sums are calculated. So here's a simple one. We're looking at simply the squaring function, f of x equals x squared over the interval from 0 to 2, and we're going to do a uniform partition with, well, first 6 rectangles, and then we're going to generalize to look at n rectangles. So just to kind of give us a visual reference here, right, we're looking at this situation here. So here's 2. So in the first one we're going to do 6 rectangles. So we're looking at something like this, and notice that because we're dealing with an increasing function, we are getting an overestimate for the area, right? We're choosing right endpoints at each on each subinterval, and so each of our rectangles kind of comes above the graph, so we're going to get a little bit more area than we should. We could also look at what happens if we do left endpoints, so we can get both the kind of upper and lower sums, the overestimate and the underestimate. Okay, so let's do 6 rectangles first. So what's our delta x? Our delta x is 2 minus 0 over 6, which is a third. Okay, our points are x0 is 0, x1 is a third, x2 is 2/3, x3 is 1, x4 is 4/3, x5 is 5/3, and x6 is 2, is our right endpoint. Okay, so that's our partition, and we're taking ci to be xi in each one. So our Riemann sum looks like this. Okay, it's going to be the sum I going from 1 to 6 of xi squared, right, because that's my f of x. My f of x is x squared, times 1/3. So this part here is my f of ci, because I chose ci to be xi. The 1/3 is my delta x. Okay. So what this gives me, and notice that the 1/3 is common, right? So I can put the 1/3 out front if I want. So I'm going to do 1/3 squared plus 2/3 squared plus 1 squared plus 4/3 squared plus 5/3 squared plus 2 squared. That's my sum. If I want to, I guess I could work this out. If I pull out the 1 over 3 squared, 1 over 27 times 1 plus 2 squared is 4, plus 3 squared is 9, plus 4 squared is 16, 5 squared is 25, 6 squared is 36. And I suppose if we wanted to, we could add all those up. 36, 40, 50, 75, 85, 91, 91 over 27. I think that's about right. And we could always, we could work that out on the calculator, figure out what that is. If we had done left endpoints instead, well, then the first term I would have put in would have been a 0, right? I would have a 0 squared at the front, and I wouldn't have the 36 at the end. And you can see that I would, in fact, get a much smaller number, right? I would have to drop this 36 off the end. So I would get an underestimate that's much smaller. If we went with n rectangles, well, now my delta x is 2 over n. My x sub I is 0 plus I times delta x, which is simply 2i over n. And using right endpoints, so f of xi, which is xi squared, that's going to be 4. 2 squared is 4, I squared over n squared. So my Riemann sum looks like this. It looks like the sum, I going from 1 to n, of 4i squared over n squared. There's my f of xi times my delta x, which is 2 over n. And at this point, there's not much else that you can do with that. I mean, you could simplify a little if you realize that really the only thing that isn't a constant common factor here is the I squared, right? The 4, the 2, and the n's I could pull out. I could write this as 8 over n cubed times the sum I going from 1 to n of I squared, right? So you can pull constants out of a sum, right? Essentially all you're doing here is factoring. And actually there is one more thing you could do here. If you look up properties of sums in the textbook, you will find that there is a summation formula that says the sum, I going from 1 to n of I squared, is n times n plus 1 times 2n plus 1 over 6. You don't need to know how to come up with that formula. In fact, you don't even need to memorize it. Don't worry. You'll use it once on assignment 5, your 5th written assignment, but I don't expect you to memorize these formulas. But you could actually put that in. If you know the formula, why not use it? 8 over n cubed times n plus 1 times 2n plus 1 over 6. And then from there you could even clean this up a little bit, right? You can see that you could cancel one of these n's with that one. 8 over 6 is 4/3, and then I have n plus 1 over n, and then 2n plus 1 over n. And actually we can simplify this even a little bit more. If I divide each of these terms by n over n is 1. Okay, so I have 1 plus 1 over n, and similarly here I could write that as 2 plus 1 over n. And now you can see what happens as you take more and more rectangles. As you take more rectangles, 1 over n is going to get much smaller, right? This 1 over n is contributing to this overestimate. If you had done left endpoints, you'd find that you had a minus 1 over n there, or something roughly along those lines. Right? If n is large enough that you can ignore that 1 over n altogether, you can see that what you would end up with is you'd end up with the 4/3 times 1 times 2. You'd end up with approximately 8 over 3 if n is large enough. And not surprisingly, that 8 over 3 is the value you would get for this integral were you to do it. Okay. One more. We'll do the setup again, and we'll look at this, and then we'll leave it at that. We won't actually be able to do anything like we did with that last one. We won't be able to simplify quite the same way, but we'll try it anyway. So delta x in this case is pi over 6, right? The interval has length pi. We're dividing into 6 rectangles, so x0 is 0, x1 is pi over 6, x2 is 2 pi over 6, which is pi over 3, x3 is 3 pi over 6, which is pi over 2, x4 is 4 pi over 6, that's 2 pi over 3, x5 is 5 pi over 6, and x6 is 6 pi over 6, which is pi. Okay, so again, if we use, now in this case we use left endpoints, right? So my sum looks like this. The sum, I going from 1 to 6, f of xi minus 1 times delta x. So this looks like this. It looks like cos of, so when I equals 1, we get x naught. We get 0, and then cos of, we do the next one, pi over 6, cos pi over 3, cos pi over 2, cos 2 pi over 3, cos 5 pi over 6, and we multiply that whole thing by delta x, which is pi over 6. And I guess we could evaluate, but there's not much we can do with this sum here. 1 plus root 3 over 2 plus 1/2 plus 0 cos of 2 pi over 3. Actually, that is going to be minus 1/2. hey, it actually simplifies quite a bit. Minus 3 over 2 times pi over 6. Not so bad. Pi over 6. We can do that. Okay. We could do it for n rectangles, but this time we'll find that we're not going to be able to evaluate things quite so nicely. The best we can do here is say, well, the delta x is going to be pi over n. Ci is going to be xi minus 1, which is pi times I minus 1 over n. And so our Riemann sum looks like the sum I going from 1 to n, cosine of this I minus 1 times pi over n times pi over n. And there's not much else we can do with that, right? There's no way to really, 6 rectangles turned out to be a special case where I could evaluate cosine at each of those points, and things actually simplified quite a bit. In most cases, I'm going to be stuck. There's not much I'm going to be able to do if n is, say, like 100 or 200 or 1,000. There's not much I can do, right? There's not much I can do to simplify that sum. And so one of the things you realize as you start looking at a few of these Riemann sums is that this is not a method that we're going to want to use going forward to evaluate integrals. We're going to use these Riemann sums to define integrals, but they're pretty much useless when it comes to evaluating integrals. When we want to evaluate integrals, well, for that we're going to need a theorem. We're going to need the fundamental theorem of calculus, which is coming up pretty soon.